cosmic storm. Floating on whimsical wavelengths is the norm. Dancing through the stars, chasing spectrums of light. Riding the waves that are just out of sight.
Mars on Mars. Say that 10 times fast. It's time for Whimsical Wavelengths. Today is looking at volcanic eruptions on a neighboring planet, that being Mars. Looking into the rock record is always like detective work, collecting measurements and clues to slowly piece together the past. Doing that on another planet is even harder. No one is there to pick up samples or walk the outcrops. The first word that started this episode, Mars. M-A-A-R-S. So no, not the planet. Mars, we have them here on Earth. They're formed by violent interactions between rising magma and subsurface water or ice. Okay, like a lot of things, the name sort of hides a few terms. If I would expand it a little bit, the full phrase for this type of volcanism would be Phreatomagmatic Diatreme volcano. Yeah, a mouthful. Let's break that down a little bit. The first word is Phreatomagmatic. Phreato is a prefix coming from Greek pertaining to water. Magmatic? Well, that's magma. Hot, liquid rock under the ground. So this first word indicates steam explosions, which include magma. If you're looking into this on your own, you'll probably see the term phreatic eruption. This is still a steam explosion where the heat is still due to magma beneath the ground, but no magma was included in the eruption. Yellowstone's geysers and the occasional bigger explosions from that same system fall into this class. Maar is a description of the geometry as well, or the deposits left behind, because they leave a broad, relatively shallow depression that cuts into the country rock. So that's just the rock that was already there, often below the original pre-eruptive surface. So they'll show up as kind of like holes or depressions. These features get shorthanded into Mars in both the literature and in common speech among us volcanologists. Finally, diatremes. They're the broken pipe or carrot-like shape left behind by the rising material that erupted. From Kilauea to Messiah to the Cascades, we've covered plenty of volcanic styles on this show, but this one is new to Whimsical Wavelengths. We'll get into so much more in a moment when our guest arrives, but I feel it's important to iterate on one thing. Finding them doesn't just record an eruption. Remember, you need groundwater, so they record part of the environmental conditions at the time they occurred. If you could find evidence of them on Mars, the red planet, you could infer environmental conditions on a distant planet when that eruption occurred. Constraining past environmental conditions on Mars, that would be huge. If Mars, M-A-A-R-S, really existed on Mars, it means the god of war might have had to share the stage with the god of fire. Mythologically awkward. To discuss volcanoes and the hunt for them on Mars and what we can do with them. All right, so please welcome to Whimsical Wavelengths, professor at the University of Missouri, Kansas City, Dr. Allison Graettinger.
Hi there.
And you know what? We met way back in 2007, I think it was. I think we might be getting old. At Messiah Volcano, where both of us were volunteering with Dr. Guillaume Marie. You also, like me, volunteered at the Hawaiian Volcano Observatory as well. How did all those things come together? Was it like a high school straight into volcanology, or like from a little tiny kid like wanting to poke lava with a stick, or was there like a meandering path?
I might not have been that ambitious when I was little. I definitely wanted to be covered in mud as often as possible. But I was lucky enough to meet somebody that told me geology was a thing. And how do I get there was chemistry and geology in high school. Didn't have geology. So when I finally took my first geology course, it was sort of a trust this process and dove right in college. It worked out. And my professor eventually told me that I could study volcanoes. Like that, I needed permission, apparently. I thought that was made up. It was a thing in movies. And he's like, no, you don't want to just do petrology. You know, I don't want to just study crystals and things that I can't touch directly. He's like, go play with volcanoes.
Wait, he actually said that? You didn't actually ask? He was just like,
No,
you clearly like volcanoes. Go. Go. Have fun.
Right, because I was asking about grad programs in igneous petrology, which would have been behind the microscope. Some fieldwork maybe, but he's like, no, that's not right for you.
No.
So it's somebody who a faculty member who listened really well, and I will always be grateful for that. Because then I was brave enough to run off to New Zealand for a master's, which was wild. But that was partially because I had bad test scores, and New Zealand didn't care about my test scores. And so when I didn't get some perfect shiny position in the US, I ran off to New Zealand, and they happily trained me up from where I was to the next level. And to get to Nicaragua, I was just on a mailing list. And again, it took a bit of a leap of faith that, like, come meet us in Nicaragua. And it worked out, and I now still talk to you, and I talked to some of the other folks who went with us, and I just got to see Guillaume last summer, which was awesome.
Awesome.
So,
I miss that guy.
Humans are such a big part of our journey. Like, you can't have a perfect path. Life, of course, intervenes, but it's the humans who can help you see what you don't see, or to trust you and take you to the next level, or say, here, go hike through that gas plume with a battery on your back and dig some holes and see if you like it.
And to be fair to all those listening, that is almost exactly what we did at Messiah Volcano. I don't remember the battery so much, but I do remember the wire, the tools, the electrodes, and the gas plume.
We had a magnetometer for a day. That's why we had a battery.
Yeah, there was a magnetometer for a day. It was a lot of really dusty, sweaty work, because at that time in Nicaragua, it was the dry season, and every time you dig, there was like this puff of both soil and ash that kind of wafted out over you, which stuck to your sweat, and so you had a number of different colors by the time you got home due to SPF dirt, as I like to call it.
It was effective against UV. I was grateful to it.
We're here to talk about Mars, and I'm pronouncing that right. It's Maar.
But it's still Mars. You can blame the Germans because the type locality, or at least the first location, was in Germany, and so that was the name given, and it stuck.
Well, I'm all for whatever name as long as it stays consistent. As maybe one of these days I'll get into with diatremes, which we will also be talking about, but dimoniferous diatremes. They have all kinds of weird terminology that doesn't exist anywhere else in volcanology, which drives me crazy. But I'm already convinced as to the reason why we need to study Mars. I'm biased. All things volcanic, or basically all science, really. But for the listener, what makes sense why are these like important to study broadly? Yeah,
so the whole reason I'm interested in Mars is they look unassuming because we frequently discover them as these shallow sloped rises with a little lake in the middle, and they're frequently completely covered in farmland or pastoral grasses, and it looks non-threatening. However, the eruptions that formed them, that made that hole in the ground, were explosive. And if we are overlooking them, we're missing out on a pretty significant hazard. Now, they aren't the most frequent of volcanic activity, but it's one of those high-risk scenarios that if it does happen, it's a big enough problem that we do need to understand where they are, how often they occur, what else could happen besides the Mar, what other types of eruptive activity, and how to better prepare in the future. All of that comes from just staring at what already happened.
Okay, so how big are we really talking about? If they're a hazard, we're not talking about Yellowstone's geysers throwing some rocks in the air. We're talking about something much more significant than that, aren't we?
Right. You could potentially have an eruption that's as small as the geyser scale, where rocks are thrown a few 100 feet or tens of meters. But more likely, we're going to deal with particles going 1 to 2 kilometers from vent. And if there are pyroclastic flows, they're measured anywhere between 9 and some studies suggest maybe 15 kilometers from the source. Now, one of the other problems is that source, the point where you're like, okay, that's where the bad stuff comes from, and we're going to measure a buffer zone around that moves during the eruptions, and that's something I've spent a lot of time looking at, and they can move several kilometers within it, which means your hazard zone's moving. And there's also the possibility, if it has a tall plume, some of the few historic eruptions of these we've seen can have quite tall ash plumes that would then affect air traffic and then blow ash and dust downstream. Now, it's not going to be the biggest, scariest eruption, but they're frequently in locations where you don't have the smoking gun, as it were. It's not, you can point over and say, that big cone, that's the problem. They tend to be in distributed volcanic fields, wherein we have a bunch of little cones and we don't quite know where the next one will be. And so preparation's even harder. So your threat zone might be smaller once you know where it is, but half of it is not knowing where it is within a several hundred square kilometer area. Suddenly it makes the whole problem larger, even if the individual eruption, if conveniently located, might only affect a few people, but if inconveniently located, is really bad.
Okay, we're going to get off topic already, and I love it. So that's not exactly where I thought this was going to go. I got two questions. First one's probably quick and easy. Like, how big of an eruption could we be talking about here? Like, are we talking Mount St. Helens size? Like, that's what, 1 cubic kilometer in 1980? Or are we talking something half that size? Like, base it off a Mount St. Helens scale instead of the
right.
network.
So 1 cubic kilometer worth of melt is probably the biggest that we would expect for these types of eruptions. And most of them are smaller. So we're probably talking one step down on that volcanic explosivity index to, I guess it would be a 4 on the VEI scale. So volume-wise, individual eruptions, not that intimidating. We call them small volume volcanoes as one of the many designators when we're sort of lumping in, say, a scoria cone or a maar, or we also have a handful of sort of in-between features where if the maar is this excavating volcano and a scoria cone's a small volume constructive eruption, there's some in-betweens that we can get into if you want, but we can also just leave on the side for now. Think of it as a continuum. It's
yeah. It's like this in every science. The deeper you get, the more messy it gets, I think.
Mm-hmm.
But I wanted to get into something messy as an aside because you mentioned distributed volcanic fields. Now, the vast majority of listeners are going to be familiar with the Cascades. They have these locuses or concentrated points of stratovolcanoes. They're all concentrated. There is a section in the Cascades which is not so concentrated, and that's around South Sister in the Bend area. I can't remember off the top of my head what that field is called in around Newberry there.
Well, there's the boring volcanic field, which is Bend, and then there's the cluster south of Newberry. There's also some to the north. They're kind of scattered behind the arc. If you think of the main chain of volcanoes as the arc, then behind that you tend to get little clusters. And there's hundreds of them. And sometimes they're in well-known groups like near Newberry. And sometimes it's one or two little dudes hanging out by themselves. And so when they're next to the Cascades like that, they kind of get lumped in some of the maps we make or when we're doing hazards. But there are also distributed volcanic fields that are further from an obvious tectonic boundary. So in Utah, in Nevada, in Arizona, California, we've got some of these distributed fields is kind of the term we're leaning towards right now, where the majority of activity is one of these small volume vents of a range of different eruptive styles, and they're scattered around, and there can be several hundred over a broad region. Or you can get into Colorado where there's like 3, and they still need to somehow be compared to something. So that's why we use this term.
Right. But the more long-lived ones, not necessarily the Cascades. I think there's lots in Mexico and New Mexico as well. Like, what creates like these long-lived, what's process-wise, like creating these distributed volcanic fields?
Yeah. So we need 2 things. We need a system for generating magma, and then we need pathways to the surface. So frequently these are occurring in areas of extension where the crust is being pulled apart and we have slight depressurization of the mantle beneath it, which then there's faults and fractures created by that extension, which tend to dictate the position of where these volcanoes might be above them. And so behind some volcanic arcs, we get that extension. Sometimes there's larger tectonic processes like the basin and range. In New Mexico, a lot of the distributed volcanic features are associated with the Rio Grande Rift, which is a slightly more concentrated zone of extension. We could leave North America And there's examples in South America, there's in the Philippines. You can basically find them on most continents. France has some older ones. There's examples in Spain that are also older, but related mostly to extension, though that extension could be connected to subduction, or it could be other tectonic processes. The challenge to remember with Earth and plate tectonics is that they're all happening at the same time, and any bit of Earth has had a long volcanic history, so they could be really old fractures that are being leveraged. They could be reactivated due to some new tension related to a different tectonic process. And that's where we find these, is sort of complicated adjacent tectonic provinces that usually are more extensional than not.
Okay, so for those who need a refresher course, you can go back into the Whimsical Wavelengths episode library, and there we've talked about how we generate magma lots of times. So let me just rephrase this, and hopefully I've got everything we can summarize and then move towards the paper, which is on Mars. And I meant the planet, not the volcano. So I guess first thing we need is some kind of feature that allows more magma to come towards the surface, usually extensional, usually as part of some other system, often to do with back arc basins, so you could be getting a number of different sources as to why you have an increase in magma there. And it's distributed, so it's not coming out as a locus. And I think there's one part we missed, is that you need to have some kind of shallow groundwater to have the interaction.
Yeah, we hadn't actually hit the part about why we have excavation with these, is that it does need to interact with groundwater or ground ice. And that water can be in your traditional aquifer, in some nice stratigraphic unit, water hanging out between sand grains, or in faults. Can be also associated with things like permafrost, or if you have a swampy environment, you can also create this kind of feature.
So the idea here is that you interact with enough water that it all flashes to steam, and that steam needs to expand, and then it expands so fast that it causes failure of the rock?
This is the fun part where I can say yes and.
Oh.
So steam we know is powerful. We've made engines based on this steam expansion, right? It does a lot of work. But one of the fun things we've gotten to learn by taking molten magma and trying to blow it up is magma plus water does not automatically make explosion. If you've ever watched some of those fun videos from Hawaii where lava is going directly into the ocean, we also had videos of this from La Palma in Tenerife, the Canary Islands in 2021. It doesn't blow up all the time. It kind of waits. It's intermittent. So what's different? So it's not strictly only steam expansion. The steam's definitely contributing, but there is a heat transfer process that is faster than even steam expansion, which is kind of mind-boggling when you first encounter it. But this transfer of heat away from the lava into water. Water is the most efficient coolant we are aware of on this planet. It's one of those reminders that like Earth is wild because we have all this liquid water, which doesn't behave like all other materials, right? Like when you freeze it, it becomes less dense, which is unlike most other materials. And when in its liquid form, it's this really effective coolant. So it sucks the heat out of the lava fast enough to shock it. And that shock then releases mechanical energy. So it's a thermomechanical shock that results in the production of shock waves, which breaks more things, which lets more water in, which leads to more shocks, which also produces the steam. So this combined leads to a faster explosion than you can produce in other magmatic systems.
And there's like a sweet spot with water pressure, I gather, like depth inside the Earth or depth underneath the ocean.
Yeah, so the heat transfer happens when you have liquid water in touch with the magma directly. But as anybody who's ever thrown a little bit of water onto a frying pan has seen that formation of vapor or steam occurs rapidly and then actually insulates the water from the pan. So then you have this little dancing water droplet, or the Leidenfrost effect. That water vapor actually is why most magma-water contact is kind of meh. And maybe some steam is produced, but if it's not trapped or anything else, it's not necessarily dangerous. And this is one of the reasons that these eruptions are so interesting to me, is understanding both the physics of it and the consequences. And so when the vapor film's not there, it should be more explosive. So you could think at those great pressures, shouldn't it be, if there's no vapor forming, shouldn't it be explosive all the time? Also not necessarily. So there's still something we're working on, the conditions that are ideal for this rapid heat transfer, and the balance of energy release from the different aspects of it. But experimentally, we sort of played around with water temperature, salinity. All of that does act as a knob on how explosive this is and how much of that magma temperature, that heat available in the budget, gets turned into explosive energy. And the answer is it's not very efficient. It's just really dramatic for the amount and the speed at which it happens. So the depth beneath the ocean is going to affect that, the availability of water in the system, but it's not some perfect ratio. So we had some sort of starting models and we're like, this sounds reasonable. But of course, as you said earlier, as we dig into it, it gets messier and messier. And how do we turn this into usable science, right? That can help us be safer, that can help us to plan for it, or, inspire some weird new steam engine of the future.
Speaking of steam engines on Mars, I guess these sorts of things are really important to recognize in the rock record because it tells you something about the environment, right?
Absolutely. It's a great way to reconstruct other aspects of it besides just the magma.
Okay, so one last stop before we get to the paper. Mars locations, volcanic locations all around the Earth, there's a database, a shape database to help you kind of like find them. Do you also train this on AI as well to be able to search the Earth for these types of shapes?
That's a great next step. So I call it the Marvelous database because it's Mars, volcano, location, and shape. And one of the things we had to figure out is like, are all Mars similar? And so we just started looking for the prettiest ones around the planet. And I think we have a pretty decent catalog at this point. There's about 435, and all continents are included. We know there's more, but geology loves to rewrite the history that it's leaving behind, so some are missing. And I continue to have students helping me with this. We're still doing it manually because while circle recognition, pattern recognition is actually a great application of machine learning, we need a proper training data set. And 430 is a little on the low side for a solid model. So I need to also have good databases of what I don't want as a way to rectify the absence of sufficient quantity of the variability we could find in the original data set. At least this is what I've been told by my colleagues when they're like, you should do machine learning. And I said, here's my data set. And they go, ooh, we need more. So we're doing it the old way, or the old-fashioned way, which is hunting for them using people's papers that have said, we know this is Mars, somebody's been there and checked it, hunting through Google Earth and then trying to back that up so that we know that feature's what we think it is. Because fascinatingly, Earth's really good at making circular lakes. There's other ways to do it. Glaciers, melting permafrost, meteorite impacts, anthropogenic things. We like circles as humans, so they're out there too. And so this is the challenge also once we leave Earth, is there's other circles out there, and how do we tell them apart? So we need these sort of anchor points of confidence, and that's what Marvelous was hoping to be. And in future versions, I'm trying to add in some of that continua I told you about, where like they're not all exactly the same. And the fun thing is, while they're circles, they're not just simple circles. Sometimes they look like Mickey Mouse or a peanut. It's compound structures. And that's when I got really excited about looking for it elsewhere. Are we ready to go to Mars?
Have you thought of trying to do machine learning in a slightly different way? Instead of only building a giant database, using that database of what you have and overlaying it with other layers like heat flow? So the machine learning can make the inference or tying things like heat flow or structure to the circles themselves, and only where it finds the same pattern that it can pull it up.
Right, having multiple tie points. We haven't found the right companion data set.
It could be multiple. I mean, we use lots in mineral prospectivity.
Yeah, so I think that is a next step, and it's a combination of finding the right data sets, finding the right partner, and getting them to trial it. And it's been the folks who were keen had an existing workflow. they wanted to throw me in, and that's where
It's
it
not
didn't
gonna work,
align
yeah.
yet. So what I keep doing is trying to look for other patterns in it. So that's the other benefit of Marvelous, is in addition to its location and its shape, we're keeping track of age, we're keeping track of composition, we're keeping track of regional context, and I tried things like latitude, longitude, elevation, and we're sort of iterating, and we keep going back to fill in more of these data sets as things get published or people send them to me. And that way we can look for additional patterns besides just where they are to evaluate if there's something else useful hidden in it. So I tried tectonic setting. I tried, what we really need is more age and more compositions. And I think that might be where we find this companion data set that you were talking about that we could use as a separate check. Heat flow is hard on these because there's no magma source anymore. They're done.
Right, if it's old.
It's and they're all such small volume that their thermal signature would be quite little.
I was more thinking heat flow is like a regional scale. So if you're looking for something that is potentially active in the Holocene, then you're going to have a increased heat flow of the whole area. For instance, the Cascade Arc has a high heat flow, right? So that way when you're telling to search the whole world, it's not like going to Kansas and going, well, there's a circle there. You're like, well, it has no heat flow, so it won't exist type thing.
But we do have some fun diatremes there that are not Mars. They're
Kimberlites?
yeah, but non-diminiferous.
Yeah.
Yeah. Anyway, we're off topic.
It's okay. That's the whole point. That's why I have a skeleton of a blueprint, and I'm moving.
Thermal inertia is the fun one. And planetary scale, it's actually easier to do thermal inertia on Mars than it is on Earth.
Huh.
There's just a lot of
What? Okay, well, we're switching to Mars, and I'll come back to that in just a second, because the paper at the heart of this episode is identification of candidate Martian Mars in the area of Coles and Nephenthus Amethys. I pronounced it wrong, that's okay. With the extension to Mars as a proxy for groundwater and ice depths. So Mars, the red planet. And I think we've already stated why we want to look on Mars. I mean, we want to find water, we want to find what happened to Mars over time. But thermal inertia, what is that in context of a planetary scale?
Yeah, so we can look at the daytime thermal emissivity of a planet. That is the long wave infrared wavelengths. So imagine like those old coil stoves. I know some folks still have them, right? That heat energy come off it. You're actually seeing it glow red. That's the emissivity. And so we can measure that in the day and we can measure that at night. And so as the sun's hitting a planetary surface, rocks warm up, soil warms up, the whole surface will. And depending on the material properties is how long it's going to keep that heat or how rapidly it's going to change. And so dense materials take longer to heat, and loose materials, soils, dust, etc., are going to change temperature more rapidly. So if we're looking for volcanic deposits, we would expect them to be loose materials. If we're looking for lava flows, we're expecting them to be dense. So they should have different thermal inertia, which is basically comparing that day-night pair. So what's fun now with all the satellites we have living at Mars collecting data, we have a pretty decent planetary scale thermal inertia data set. And so that can be useful for looking at changes in basically material properties across the planet. On Earth, we have lots of moisture in the soil and plants and things like that make thermal inertia a little messier. It still can be used, but it's not as easy for a whole planet-wide comparison. But there is some problems on Mars because there's lots of dust moving around on the surface. So it's still a geologic environment and still messy in all the ways to make our brains work harder.
That's awesome. Okay, so back to Mars. We have volcanoes and we've had water on Mars. This is what we infer from the data that we have. So those two things are similar to Earth. But what about that volcanic activity in and of itself? Is that volcanic activity similar to Earth? And what does gravity have to do with it all? I mean, are there any other things that are different with respect to Martian volcanoes and the processes that'll affect a Maar-type eruption, such as gravity? Like, would it change its shape? Because if shape is how you're identifying them, what's out there that's going to change how you look at them?
Okay, so I won't answer all the questions you just opened because some are rabbit holes. Let's stay focused. I'm going to try.
Yeah, sorry. Sometimes I'm my own worst enemy.
Well, and also, as I can't turn professor off, I always have a need to make sure there's a root understanding. But let's stick with Mars on Mars. And can I really play this game of, I know what they look like on Earth, so this is what they should look like on Mars, right? That's a great question. When we're thinking about it, our ideas of magmatic compositions for Mars, we're expecting them to be still similar. Silicate melts, probably pretty mafic, based on some control data we have from meteorites, from satellite remote sensing that indicates we should expect some nice runny silicate melts like on Earth. So for the majority of Mars, which have that composition, that's not a problem. As the magma rises and encounters groundwater, or ground ice might be the case on Mars, and it explodes, it's then going to be lifting rock above it. And so your question was, does gravity matter? Yes, but what's it going to do? So we have a good idea of like ballistic particle, like take yourself back to physics, right? When you're just like, if I throw a rock from here, it's going to fly in a parabolic arc, and gravity is one of those major controls for how far away it can go. So that should influence it somewhat. But the challenge I was trying to point out earlier from a hazard perspective is that it also moves. So if you have a point source and you see how far away things go, you can back calculate that source location. But if that source location likes to move around, a little do sideways, vertically, left, right, east, west, north, south, all the options are possible. When you look at that deposit, you start going, well, is it actually bigger or smaller than on Earth? Generally, most things Martian are bigger, so that's a good go-to. So my search parameters, I was like, I'm just going to look bigger than I expect on Earth. And also, atmospheric pressure is different. So that's going to affect things like drag, which is again going to influence whether you're going to produce big poofy columns of ash rising that could collapse. Are we going to have more things just going up and right back down? It's going to affect some of those physics that would affect the distribution of material around it and how steep a wall you can keep in your hole in the ground. So the answer is yes, but unlike with scoria cones, where we're mainly just piling up debris around a point source, it's harder to just adjust the model. So it comes back to, let's look for them and see what we find, knowing that we're going to have to look a little bit broader than what we see on Earth. And the main tie point why I felt confident that I could do this goes back to that Mars aren't just circles. We have circles, but it's something like 13% or less of the database were simple circles. And so that leaves us the majority, which are compound structures. And of those structures, when you can see that it's intersecting circles like a little mouse character with a copyright on it that I don't know if we can name, nuts.
Yeah, we
right?
can. The original has entered the common
you're
license.
Right. Public domain. Okay, so if you have a Mickey Mouse shape, or if you have a snowman where you have these overlapping circles and you can recognize those discrete circles, that is a unique shape. Other holes in the ground on Mars, especially impact craters, which are all over the place, they tend to be more elliptical to circular. The vast majority are circular. Funky shapes do exist, and a lot of the funky shapes we find tend to be volcanic. So we're going to look in a specific size range, slightly augmented for Mars. We're going to look for them being distributed, so not all on some larger edifice, but sort of spread around, and ideally with other volcanic things with them. So I found, we started in Arenicolis because somebody else said, I see these cute little cones that could be scoria cones. Maybe they have a little bit of magma-water interaction to make them have bigger summit craters. And nearby, I saw these really big holes, some of which looked like compound circular structures. And I said, okay, how many can we find? And we were inclusive at the beginning, and then we made this checklist of what is an inclusive criteria versus something that's going to exclude it. And so I had to get to know impact craters better, especially when you have an impact. The debris that flies from that can also make impacts, and those are messier than the first one that's flying at the really high velocities. The secondary craters, what they're called, are a little bit more irregular, but they tend to all radiate away from some point source. They tend to be really asymmetrical, where a lot of the debris is on one side and not the other. And so we could use that sort of contextual information to check off what was a good candidate from something that is probably something else. Did I actually answer the question? I don't know.
Yeah, and almost answered the next question too. Okay, first off, how many did you find?
So we started in the order of like 70 holes in the ground. We're like, we have holes. And then we narrowed it down. And so there's 12 that I think are meeting the criteria. And what's exciting about that is so far there isn't a better explanation for them. Now, I'm one of the few people who've stared at them closely, and somebody else could very easily come in and look at them and spot something I missed. But that's the fun of science, right? Is like I get to make this list and say, all right, here you go, guys. Go check them harder. Let's see what else it could be. And I also have people who are like, okay, based on your rules, I'm going to go check my holes in the ground in a different part of the planet, and we'll see if this system works elsewhere. And it's kind of fun to wait and see, ooh, I wonder what's going to happen. And the longer people go, well, seems reasonable, you kind of go, really? I thought I would. It's on another planet. I'm nowhere near that. But we can try that. And it's a great opportunity for testing my models about Earth. It's a great opportunity for us to think about how well we understand those other processes that I was excluding. And even that little bit of going outside of what we know to like maybe still helps us learn and is part of this whole scientific endeavor.
Okay, well, taking this full circle, how does this now change your thoughts when looking for this stuff on Earth?
So we've had some questions about the role of ice versus water. And I wanted to do some experiments, and we've sort of goofed around with lava and ice. I'm saying
Wait. You goofed around with lava and ice. I never thought I'd hear that as a phrase.
The reason I'm using such a flippant term is it's sort of the preliminary tests to see what's feasible before I get into some really rigorous, we're going to test all these variables. Because I've worked with molten lava between 60 milliliters and 60 liters in dry and wet conditions. And we had some pretty good constraints on how it's going to handle so that we could design the experiments and then iterate through it. So we were looking at the roles of like porosity and permeability. So how the water's in the material that's hosting it and whether it can move through it so that we could understand steam formation and how this moves around. And we're like, all right, so when we do ice, how should we do this? And I made what I call sediment popsicles and just froze sediment and water together. And to control how much we had, I said, let's go ahead and just saturate the sediment, right? So there's just as much water as can fit between those particles, and then we freeze it. And I was thinking, when we did plain ice experiments where it was lava plus water, the ice melts, we have to capture the water so we could calculate the thermal budget, how much energy was put into melting the ice. And so we spent an hour or two to try and slope the whole surface to catch the water in a bucket. And then there was no meltwater because with the particular sand we were using, the permeability is really low. So the steam sort of forms and stays in the sand and then eventually leaks out. So there's no water pouring out of the system. Oh, okay. So that's what I mean by goofing, because we have to do some of this initial testing to be like, well, what are we going to measure when we want to be able to say something systematic about this? So we haven't done nearly as many as I'd like to start calling it a true experiment yet. But in that process, and in the process of looking at Mars, thinking about, well, what's the difference when it's solid and needs to be melted? Because ice is not as good a coolant due to it being solid and water having the right heat capacity to be able to transfer energy so effectively. So we still have to melt it to get the fun interactions or the dynamic interactions that produce these explosions and could excavate the ground. So that step matters. And it's forcing us to then go look at Earth and we're like, well, where did we have ground ice? We know it's happened on Earth. There's the biggest in the world, actually, are 6 kilometers across.
Holy
in
smokes.
the Seward Peninsula of Alaska. And are they big because they're permafrost, or are they big because of other things? And is it permafrost during the eruption, or is it permafrost melting afterwards? And of course, this being out in the rural Seward Peninsula, this is like helicopter work and bears, and there's all these massive lakes, and it's boggy, and you're not getting there quickly. So there hasn't been as much work on them. So then I started going, well, are they in the rock records? And now I'm going back to Marvelous, and I'm looking for how many occurred in older permafrost that maybe isn't permafrost right now, and we can go work on it without damaging it or being at risk of bears.
Is there enough methane in the permafrost there? Just randomly came to my mind.
Right. What does methane have to do with the story? I don't know.
For listeners, there is the ability to store a lot of methane in permafrost. In fact, they have methane explosions in some areas of Russia that they have craters for that are not volcanic.
Which make fun holes in the ground.
They do.
What makes them different? They tend to not throw out as much stuff, so they don't have as big a crater rims, but I had to go through that exercise. So, like, I want to be a volcanologist, right? I care about... But think of all the things in just this conversation we've had to get to solve this problem, which is why I love it. Because I'm forced to learn about periglacial environments, which is, near glacial environments, permafrost, methane explosion holes, and then thinking about what would these other compounds do. And if we want to go even more complicated, on Mars, they have CO2 ice. So if we're dealing with CO2, how well does that work? I haven't goofed with CO2 ice and lava yet, but I will someday in my career. Or somebody else will, and they'll show it to me, right? So I could wait for somebody else to do this. There's only so much time one human can do, and so it has to be this collaborative effort to get all of the fields we need, the physics, the geology, the atmospheric science, the planetary science, the organic chemists, right? Like, we have to have friends, and we also have to chip away at this big problem. So that's why I like experiments. That's why I like planetary, because it feels very tangible about how you're pushing our knowledge or testing something. And sometimes that can be harder to imagine for folks who only took chemistry, and like experiments are these really set things with like an answer at the end. The experiments in geology can be me pouring lava on things, see what happens, poke it with stick, go yay. But can also be just, I have a model, does it make sense with the rocks? And we need all of those approaches. And so sometimes with planetary, you get to throw a wild idea out there, and they're like, but what if, guys? And there's sort of more freedom for that there than on Earth, where it's like you really need to get into it, but it makes you ask bigger picture questions, and sometimes we have time to, and we're so down the rabbit hole of what we do know or what we've been working on for our whole career. So I encourage anybody who wants to do planetary to see how your world might fit into it, because it will make you really question your fundamentals, and sometimes just realize, oh man, we know less than we think we do. I have work to do here, which is perfectly fine as a result, right? It's either way, you're gonna move on.
Yeah, I feel like getting a PhD was more about figuring out what we don't know than really learning anything at all. Okay, so let's just try to... I've already had you here for a while now, getting closer to the end. I feel like we need to
answer some questions. We actually answered some questions.
Hey, I've got no complaints. I also learned a lot about Mars, on Mars. I can't get over how that sounds. It's my new favorite tongue twister of all time. But one question that I think we need to summarize is, let's assume that these are Mars on Mars. Besides sounding cool, what does it actually tell us about Mars, the planet?
Yeah. So the fun thing about volcanoes for solving other research problems is they represent this sort of specific moment in time where something happened. And at that time, it's telling you about the conditions needed to make it happen. There's magma, and there is this water in whatever form it's in. And it's underground. So the next step I did in the research was like, well, so if these two things are true, constrained by my candidate Mars on Mars, can I say something about where that water is other than just down there somewhere? And this is where I had to look at the old eroded volcanoes on Earth rather than just the fresh, well-preserved ones, because we needed to look at the volcano guts. And this comes to the diatremes. So that's that subsurface structure where all of the damage from the explosion is located. And they tend to be these sort of conical, carrot-shaped structures. But the fun thing is sometimes it's like those weird carrots you get at the farmer's market, not the grocery store one, where it's got several shoots in different directions. And I needed to know, well, what are common shapes and common depths and the angles of those? And so I got to look not only at my Maar volcanoes, but I borrowed kimberlite literature, because in order to get those diamonds and the other cool minerals that are with them, we've just been excavating down and going, oh, is it straight down? Nope, it's slightly off to the side, and maybe it's three, again, overlapping circular structures. When you cut these across, you get the cross section is circular, or a series of compounding circles. And of that data that's publicly available, there's more that isn't, that I would love to get my greedy little fingers on.
Yeah, industry doesn't like to share data. Diamonds were a big thing.
Yeah, I don't want to make money off of it, but I want more data so that I can say what's reasonable. And then I said, fine, let's make a window of reasonable angles. And if you project those angles downward, how far do you have to go? And I also got to use my experimental data that involved burying explosives and saying, what shape can I make in the ground by burying chemical explosives and then digging them back up? And so combining all of these sort of disparate data sets, a little bit of geophysics, a little bit of excavation, a little bit of experimental, and came up with this window. And again, threw it out there for the other scientists to say, does this corroborate with what we're seeing from satellite imagery that's trying to use radar to determine the depth of it now? And so my cute little 12 are this little point pinning possible depths on Mars in one place. So if we keep looking and we get a bunch of pins, and then we match it with these other techniques, we can start to reconstruct, well, just how much water is still there or was there in the recent geologic past, which on Mars, recent is a little bit further back than on Earth, especially volcanically. There's not been a lot in the last 100 million years. But we can still say from the more recent geologic time period that there was ice at these depths, probably. So what else can we check it with? So that was kind of the fun thing I threw out. And what's exciting is I already know folks who are curious about testing my hypothesis. And so they're sort of keeping me up to date as they figure out how they're going to do it. And it might take a while because it's another planet. And then maybe someday a rover will drive up to one of these and poke around and help us to understand it from on the ground. Or maybe a geologist. I don't know if I'll be around for that time period, but it's kind of cool to think about, like, someday somebody's going to say, yeah, she was full of it. Or they'll be like, kind of useful.
Yeah, and you never know.
Right. You're always just like, oh, it's in the right direction.
Yeah. Yeah, that's science. That's science. That's how we do it. Wow. I think it's time for call-outs, because I don't even know how to follow that up with another question that isn't going to get us way off track and down another hour of conversation. So, do you have anything to call out? Future work, current work, favorite movie or documentary that just came out? Maybe Yellow Ducky?
Oh, I still have my duck. But I will admit that it's the 4th generation duck.
For those who do not know Allison, Professor Allison here, she, as soon as I met her, there was always a companion that always came with her in the field everywhere. And it didn't matter how terrible the environment was, whether it was sulfur directly into a volcanic plume or dragged across any number of different things. And it was always just as dirty as us at the end of the day. And so...
Yeah, the duck actually is more popular than me at scientific conferences. And so had I tried to stop bringing the duck, I probably would not be invited back. So I keep the duck.
So you get keynote speakers because of the duck.
The duck can't speak, so I have to do it for us.
Right. Wow. Any other call-outs now that I've kind of put words in your mouth?
Yeah, I mean, there's more ongoing projects. I just always like to say at the end of these conversations where I'm throwing at random things like I play with dynamite, I play with lava. If you're thinking of solving a problem, be more creative There's probably, it might involve duct tape and buckets, but it might involve some expensive instrument. It might just involve finding some friends who can enable you. Try it, because somebody trusted me to blow holes in the ground, and we learned a lot from it. And so you never know what tool is going to actually blow the whole case wide open.
Yeah, I think a lot of people, the non-scientists, really don't recognize the fact that science is a lot of creativity. When you're presented with a problem and you have no idea how to solve it, and sometimes you throw everything in the kitchen sink just to see what would happen. That's a pretty good lesson for all of us to learn. In fact, I do that in my day-to-day life, and it drives some people nuts. And I'm like, I'm just brainstorming. I didn't say it was a good idea. I'm not saying do that. I'm just saying, like, we have a problem. Let's try to figure this out. Let me just throw things at the wall.
That's where the sci-fi bad guy character ideas come from, is just talking to scientists who didn't really plan on trying some of those. But...
Okay, so we've come to the infamous last question that I ask every single guest. And if for whatever reason, which I hope you do, you come back on in the future to Whimsical Wavelengths, you'll need another joke. So, what is your favorite science joke?
So when you're trying to discuss whether or not the Earth is round, I have one argument that is a great way to end those conversations. And it's, if the Earth was flat, cats would have knocked everything off the edge already.
True story.
It just makes me happy.
I take it you have cats then.
Surprisingly, I don't.
Okay, well, thank you so much for coming on, and hopefully that means that you will get a cat in the near future to make you happy.
Well, I appreciate your time and your patience with my inability to follow a straight line conversation.
It was fantastic. And I keep telling everyone who comes on Whimsical Wavelengths, that's my job. My job is to try to keep it in a straight line. Sometimes I don't do a very good job. But this was great, and I learned a lot. Thanks. Okay, that's another Whimsical Wavelengths that has been brought to an end. And thanks so much for listening. This one was great fun to reconnect with an old colleague and chat about Mars on Mars. Mars on Mars. Mars on Mars? Mars on Mars. Mars on Mars on Mars on Mars. I love that phrase. Anyway, you can catch Whimsical Wavelengths again in 2 weeks. And we'll see where the Whimsical Wavelengths take us. Adios.
In a world so chaotic, so misbehaved, echoes of melodies remind us it's all waves. Colors weave stories painting the sky, swaying to rhythms as the galaxies fly by. See